So again, this is in real time. So the flood has now wiped out the entire southeastern United States. That would be terrifying, but yeah, there's lots of other things to be terrified about, so let's find out what they are. Let's see, let's zoom out. Tools, fly. Alright, flying into Uranus in 3, 2, 1. Cue someone walking into your room. What did you guys just click on? I'm sorry. Alright, that was just a little icebreaker to get us started here. So for anybody who doesn't know, the Universe Sandbox is an incredibly interesting game because you can, well, A, because there's no plot to it, but B, you can see, it gives you a very realistic idea of the physics of the cosmos. And not just the physics, but you can see the gravity of the planets pulling the sun a little bit, which is exaggerated in this game, of course. You can slow time down. You can manipulate things. You can see the true distances between the planets. As we zoom out here, you see just how tight the orbits of the inner planets are relative to the outer planets. You can see the incline. Oh, if I can get it right. You can see the incline, the true incline of Pluto. That's this orange line here. And just how exaggerated it is off the solar plane relative to the other planets. Which is why Pluto is, and all the dwarf planets are no longer in that category. You can see the distances between the planets, the size of the planets. So there's lots of things to do. You can simulate impacts. You can, well, as I was trying to just fool around, come up with some ideas for this video, I realized a good starting place might be a tutorial. So that's what we're gonna do today. We are gonna take a couple tutorials and get used to, get familiar with, it'll be a good refresher for me and a way for you guys to get familiar with the game itself if you aren't already. But before we do throw 5 moons into Earth's orbit, I want to take a moment to shout out the sponsor, the brand I partnered with today for this video, Into the AM. Legitimately the most comfortable shirts I think I've ever worn. So, I got this graphic tee. I thought this one was pretty sweet with the astronaut. There are actually some really cool designs on their website. My go-to is kind of basic plain and definitely with the pockets because I always have a pen. Yeah, and it's just the most comfortable shirt you guys are ever gonna wear. These t-shirts are awesome. So yeah, I'll have links in the description. I'll have it pinned. It'll be the first comment you see down there. So if you guys are in the market, please, yeah, look at this. I really like this one in the back. So Into the AM, my code's gonna be Let's Find Out, and you'll get a discount when you go there. Check them out, please. Up here, and then we can terraform some planets. Replace our sun with a black hole. See what the Dinosaur Chicxulub impact would really fairly realistically look like. So I thought this tutorial was pretty fun too, so let's walk through it together and we'll see exactly what this game's all about and hopefully learn some things and blow some things up along the way. So this is Earth. In Carl Sagan's voice, home to everything you know, every sinner, every saint who has ever lived, has lived on this earth, carried out his or her life on this beautiful, pale blue dot in the cosmos. So, naturally, let's launch the largest object series, the largest object in the asteroid belt at it, and see what happens. Alright, let me zoom in a little more. Okay. Uh-oh, I launched two. So, what would you like to happen? Let's explore what would happen. But there's other ways we can destroy Earth, too. I guess I zoomed out too far for that one. Let's, it didn't get quite to the impact there. So I love the actual impact physics. We'll check it out in a second here. And it shows you what would happen. It shows you how the propagation of energy, kinetic energy, would wrap itself around the Earth. It's really cool. So let's check it out. Let's put a moon really, really close. Oh, look at that. It's already shredding apart from the tidal effects forces. Let's put a couple. You could see just how devastating it would be. And now, mind you, I guess I gotta mention the time steps of this game. So every second in real time is an hour in the game. So this would be taking course over days right now. There would be a few hours there where some sections of the planet would still be safe. And just see these 2,000-mile wide molten balls of metal and silica, whatever the moon's made of, just orbiting in its sky. That would be terrifying. But yeah, there's lots of other things to be terrified about, so let's find out what they are. So we can pause the game. Let's choose a different object to add. Let's choose Titan. Now let's give the Earth 5 Titans. Let's put one here, one out here. Zoom out a little bit. Let's press play. So we are wreaking celestial havoc in the universe right now. So it's going to reset the game. And now we have 100 moons colliding with Earth. Alright. You know what, I'm going to go off script here, because that's never fun to stay on script too much, is it? Let's, can zoom in and out. This is cool. Yeah, the reason I wanted to do these was because, it explains to you some of the, more, lesser known features of the game, I guess. You can make double all their characteristics, the radius, the mass, the velocity, the temperature. You can add different elements to the planets to terraform them. Some we're gonna do. See, instantly the Earth is now, obviously it's heating up, it's gaining mass, it's pulling everything in. It can also, the tutorial says, teach us about Earth's climate, the importance of our sun, and lasers. I wonder what that means. Let's check it out. Let's explore the importance of our sun. So the sun is the most important. It's the primary source of light energy, which downstream of that, in the chain, the cycle of life and other processes on Earth, is it's the fundamentally the only source of energy other than the geothermal energy from our molten core. So naturally, what if we got rid of it? Let's just boop it out of existence. Tools, delete, hit the sun. There we go. Now look what happens. Yeah, it's interesting that Mercury is the closest, it orbits the fastest, so it's ejected the fastest. They all maintain their exact velocity, just in a straight direction now, with no more angular velocity. It's immediately translated. I don't know if that's the actual physics of it, but it is now linear. And you see, Neptune, Uranus they're barely changed much. They're not moving a whole lot because their angular velocities are so much slower than the interior inner planets. Without the sun, our entire solar system is unstable, unbalanced, and lacks any input of energy. Look what would happen to our Earth. We got a snowball Earth right now. So we can check out Earth's properties here. Let's check it out. A full list of editable properties, which I've been looking into. I want to do a video on the true expanse of time, from blank time all the way to the age of the universe, and future projections of the age of the universe, of how far into the future physics we can project currently known physics to see how the universe is going to evolve. Part of that was understanding what we know about the Earth and how it's evolved, and it's interesting how many large temperature fluctuations the Earth has been through, and that it's been a snowball like this. They think almost everything to massive glaciers of ice capped the north and southern poles, leaving essentially just the equator without ice for millions of years in the past. And it's just fascinating how remarkable it is, how special, unique of a time we're living in right now. And the ice thickness. Alright, you can see the surface temperature is pretty low, so it's gonna prompt us to bust out a laser. See if we can warm up Africa here. And remember, this is 1 hour every second. So if we slowed it down to real time, you would see this propagating on a much more comprehensible scale, I guess. Which I think is pretty cool, so we'll check that out in a little bit. Okay. But, look at that. You can see exactly on the surface temperature map over here where I'm firing the laser. But the Earth is still cooling because it has no external heat source from its mother star. So let's add another. What is it? Are we going to add another star here? Let's add. We're going to add another star. Let's check it out. Rigel, the blue supergiant Rigel. Now I've let these planets drift pretty far away. Let's see what happens. Yeah, you can see Earth is all the way out here. And let's see how far Mercury went. That's pretty far away. Let's see what happens if I get roughly right in the middle. Rigel is 23 times more massive than our sun, so it's going to have that much more gravity. What is, let's see, gravitational force. Okay. Gravitational force formula. Okay, it changes inversely as the distance squared. Okay. Alright. But it is directly proportional to the mass of the sun. So, okay, so it will be 23 times. Look at that. So it's already starting to make the planets do a U-turn. Its gravitational force should be enough to bring back and heat up the Earth. Now look how much further the Earth is than it was. And now instead of an hour per second, we're on days per second. Let's zoom into Earth here. Let's see if it heats up. Oh yeah. Looks like its atmosphere is completely gaseous now. So the planets are being sucked in. The Earth is much too hot. Maybe we made some mistakes, ruined our solar system by deleting the sun, but that's okay. There's always something to learn from an experiment, even one that ends in disaster. So, and it reminds you can not only terraform existing planets, but you can create your own planet from scratch. A life-sustaining world, and watch it evolve. So here they're going to walk us through terraforming Mars. Let's check it out. Let's see what happens. So we're going to add water using the planetscaping tool. Planetscape, liquid water. Let's add it to Olympus Mons. See if it gets gravity right. Okay. Yeah, it does. I guess the water is pooling around the base of it, but it also looks like it's evaporating. The time scale here is 1 hour per second, so. Alright, now we can increase the amount of water per click that we're adding to the planet. So let's check that out. Quadruple the radius of the dual by selecting 2 times multiplier. Okay, let's see. Select that twice. Aim at the planet and press to hold. Alright, so, okay, there we go. A lot more water now. Let's add it everywhere. We could definitely get a feel for where the continents would be. Which is another aspect of this game that's really cool. It has real data about the elevation of the planets. So when you do mess around with the atmospheres, the climate, the geology of it, you get a feel for just how they would look, because we have liquid water on Earth to give us a baseline elevation measurement. Even though it's a little higher at the equator, I believe. Okay, now sorry, my chair's clicking a lot. I promise it's the chair. Alright, let's see what we got here. We're gonna increase and watch it evolve. We'll watch the water evolve over years. 1 year per second. Did anything happen? It wasn't enough water to wrap around the entire planet. So it was just stayed on one side of the planet. And the water we added started to freeze because Mars, of where it is and the relative to the sun, we can try to give Mars shorter days, it says, so one side doesn't get too hot or cold, so we're going to make it spin faster. Tools of force. So here we go. Oh, and you can change the tilt too. Oh, okay. Alright, we're making it go way too fast now. It's got too much. We accelerated it. And it's just ripping it apart. Alright, so that was a waste of time. This is a pretty cool aspect where it tells you the habitable zones. This is obviously color coded where red is hot, blue is cold, green is just right. 40 light years away. TRAPPIST-1 is actually a real star that JWST has looked at, and I think it's a brown dwarf, or it's a really dim, much smaller than the sun. So all these planets, the Goldilocks zone, the orbital distance from the sun or from TRAPPIST, the star, that would be yield just the right amount of energy to allow life to form and water not to evaporate or select it, open its properties, double the mass. So now we disrupted all the planets. It's chaos. Alright, so now we have galaxies. You can even fly beyond the edge of the Milky Way to watch what happens when the galaxies collide. And we have two black holes that simulate the center supermassive black holes of our galaxies, and they just merge. But you can see the time step here now dramatically increased to 1 million years per second. So let's see. Alright, so it says, here we go, it's showing us how many different simulations it has pre-programmed that we can open up. Cool, let's see what we got here. Saturn with rings. Yeah, this one's pretty cool when you can watch the simulation. How, well, this one's just more beautiful, I guess, how a moon or a large body thrown into Saturn's rings would destabilize them and warp them. That's pretty neat. Let me see if I can do it just right. So we're going to add planets. Here we go, planets. Oh, we're going to add Neptune. That's pretty massive, yeah. We're going to add Neptune. Okay, let's check it out. Let's find out what Neptune does. It is hard to tell. Alright. Here we go, guys. Let's see what Neptune does here. It's hard to tell how far. Okay, there we go. So I did get it close enough. Now watch three-dimensionally. What happens here? So Neptune is throwing the rings out and pulling it in, pulling it up and down as its orbit, crosses the plane of the rings, and now it's throwing it out like. That's pretty cool. Sucking a lot of the particles into itself. It's just completely disrupting the ring system. A lot like you see galaxies in the pictures, but also the simulations to try to understand the physics of what goes on when galaxies merge. They fling entire tails of billions of stars out, which is that fact that's hard to comprehend. Thinking about one star is hard enough. The size, the energy, the force, the distances between stars, and then you think about billions of those stars being flung out into intergalactic space when galaxies start merging. It's something to think about. Okay, so one last note. This is the tutorial. While we watch the results of our experiment, go home, click the back arrow. Click the back arrow in the guides. Let's see what else. If you ever want to learn more about using Universe Sandbox, just select a topic from here. And then it sends us off with a nice farewell. Actually, you know what? Let's just do some fun stuff. We'll Planescape in a minute. Alright, so we got the Earth-Moon system. And for me, let's take the trails off so we don't have that disrupting us. Although it's useful to pinpoint where the moon's at. I just wanted to look at just how far away the moon really is. Maybe we'll try to superimpose it on the galaxy back there. Alright, so just look at this. I will let it, we'll put the moon on the other side. Just look at how far away the moon really is. The moon was actually out this morning, Chicxulub after sunrise, and when you look up, you know, you don't realize the moon isn't just floating, you know, about this far away. It's to really think about where that moon is. It just seems so large in the sky. It gives you an idea of how massive, how large the diameter of the moon really is. If it seems so large in the sky, yet is this far away. Alright, let's see. Let's look above it. Okay, we're zooming all the way into Earth. And now I'm going to slow zoom out. And watch how long it takes before the moon comes into frame. Right there. It's like you would normally think. I guess I won't speak for you, but I really used to think the moon was maybe here. Because when you're speaking on the scale of planets, you know, a couple Earth diameter seems pretty far away, you know, 50, 100,000 miles, but it's like 30 Earth diameters, I think. It's still not in frame. And there we go. That is how far the Apollo astronauts had to travel. It's incredible. Alright, so let's throw an asteroid into the Earth. Here's what I want to do. I want to first I want to look up the Dinosaur asteroid. Oh, look at that. Look at that. Would you look at that, guys? You type in Chicxulub and an asteroid. Flies across the screen. That really happened. It sure did. That's funny. Cute. Okay, so Chicxulub was 120 miles in diameter. It's an impact crater buried underneath the Yucatan Peninsula in Mexico. Its center is offshore, but the crater is named after the onshore community of Chicxulub, Pueblo. surprising they wouldn't have Chicxulub. I wonder if I searched for it. Could I find it there? Open. No, okay. That's weird. You would think they would have that. Alright. I'm gonna have to write them a letter then, guys, won't I? No, I love this game. This is plenty cool because you can just create your own if you really want. So that's what we're gonna do. Let's check it out. We got Alright, so let's check out a random asteroid. I think we're gonna have to custom make Chicxulub. Random rock particle asteroid. I think asteroid's probably our best bet. Alright, so we're gonna launch it. We're gonna come over here and launch it. Launch it at her. And there we go. So it's stationary now. So let's X out of this configuration. Oh, where'd it go? There it goes. Alright. Wait, what's going on here? Oh, we got launched. So we got days per second. Let's scale that way back. Oh. Okay, let's redo that. Alright, so. Okay, maybe I launched it way too quick. Let's reset that. Okay. Alright, so we're gonna we'll increase the time step to something like 10 minutes per second. Alright, let's go ahead and add our asteroid, random asteroid. And we're gonna launch it. Launch velocity. Let's see how fast Chicxulub hit the Earth. Struck the Earth. Diameter, age, coverage. Let's hit the dark reader mode for you guys so I can show you this without blinding you. Okay, so 12 miles depth. 6 miles across. Wow, the crater was 12 miles deep. That's 12 miles deep. There's a really cool video that I'd like to just maybe like comment on or something like that sometime soon. That is someone made. Maybe a lot of you guys have seen it, but someone made of the impact, of real-time impact. Chicxulub. It's a 6-hour video going over a couple minutes leading up to it, and then the 6 hours around it after the impact, and just how you can see the wall. That's a cool video. Wow, there's a lot of really cool videos. The tsunami. Okay, so the air blast pressure, air blast velocity. So just a couple minutes after impact, you have less than 10 minutes, 9 minutes after impact, you have a Category 5 hurricane radiating all. It's already gone across the entire United States. I mean, this video is just awesome. This isn't the one I saw, I think, but yeah, it's incredible what really happened. So anyways, yeah, I'd like to do a breakdown of this itself. It is incredible. You have, regions that are just set on fire thousands of miles away. Phew. So, yeah, Mount Everest, look at the bottom of the crater rebounds at 500 meters per second. 500 meters per second. I mean, it's gotta be molten at that point. The rock is just moving, it impacted, and then rebounding up. Look at that. God. And there you go. Wow, that's real time. Look at that. What is that though? A seismic wave. That B wave is a pretty seismic noise. So God, so you're already getting a pressure wave. Okay. Anyways, that's fascinating. Let's create our own impact now. Let's find how fast it was going. Almost lost track of what I was doing. Discovery. Is it here? Now this is definitely a question you can look up. Was it an asteroid? hit Europe and Africa with a 10-meter high wave, a 100-foot wave. Or no, that's a 30-foot wave. That's still a massive wall of water, traveling, what, 3, 4, 5,000 miles. That's incredible. Okay. So, we gotta pause that. Alright. 2 kilometers per second. Okay, we gotta delete that. We gotta delete that. Let's see, add random asteroid. Kilometers per second. Okay, let's add our own launch velocity. Let's 10x that. Alright. Alright, 2x. So, here we go. Alright, launch it. Oh, we gotta launch it at a steep angle, that's right. Okay, so clearly we gotta start with a empty simulation. We'll add an Earth, then we'll add our Chicxulub, and then we'll launch that sucker and watch it go. Alright, so add planet. There's our Earth. Okay. Alright, we got the Yucatan ready to go. Is there a sun? No, it's just got the lighting like there is. Okay. So now what we gotta do is add our asteroid. Let's check it out. Let's make it happen. Random asteroid. Okay, we're gonna launch. Alright. Launch right at it. I hope that that's an accurate launch. Okay, so let's select it. Change the speed, change the diameter. Where are we here? Okay. Speed. Alright. Change the diameter. 5 kilometers, 10 kilometers, okay. I'll knock it down. I'll get precise with it. Okay. It's either gonna be comically I'm either gonna have screwed up or not. I don't know. Let's find out if I screwed this up. Man, look how small it looks when you back out. Okay, well there it is. 3 hours per second. That's our timestamp, so let's... Okay, that's really fast. Let's do... a couple minutes per second. That's still really fast. Wow, this thing is moving with some speed. Okay. Well, I guess it's way further away than I thought, so we'll speed it up. Look at that thing, just imagine. Thank God we're asteroids. Man, look at it. That's pretty precise shot, isn't it? Alright. That sucker is... Ooh. You know what we gotta do? I just remembered. Oh, look at this thing. The gravity. Earth's gravity is sucking it in, too. Alright. We have to rename this. We gotta give it a proper name, don't we? Alright. Okay. It is gonna be named... Here we go. Wait, is it still going the same speed? I guess it looked like it sped up, so maybe that makes sense if it's falling into Earth. Alright. Actually, that'd be curious. That'd be cool to see if it heats up, wouldn't it? Let's find out if it does that. Let's find out how much. Maybe it loses mass. Maybe we can see the atmospheric effects of it. Alright, let's... 6 seconds per second. Let's slow this way down. Look at this sucker going. That was a direct hit. I'm pleasantly surprised. I did not think it would be that direct of a hit. Okay. Look at that sucker. Okay, so it's going... Its temperature is still way up. So... So we're going at half speed right now. 0.4 seconds per real-time second. Its temperature is negative 273 Celsius. Its radius, its mass isn't changing. Just real time. Let's see what it would look like in real time. Okay, let's get the best view here. I think a wide angle view might be best. Wait up. Oh, this. Okay. The game literally wouldn't let me pause it. That's funny. Wow. Okay, let's check out what happens with Earth. Let's see what happens with Earth here. So now let's do real time here. Let's slow it down. Okay, so we're roughly in real time, and we can see the shock wave traveling out at an incredible speed. That is ridiculous how fast it's going. So it's already going out. It's already traveled 500 miles in the first couple of seconds here. Is Earth's temperature going to increase? I mean, that's its average temperature, but let's see. looks like it peaked. It might have already peaked at something like 1300 degrees Celsius. Alright, so let's speed it up a little bit. We're going to see what other effects. So look at the tsunami effects it's already having. It's going up. Mexico, Central America's wiped out. The Gulf, the southern United States, hasn't hit Florida yet. Give it a couple seconds. Florida's gonna get taken out too. I'm hanging on. Hanging in there, guys. We see the gas pressure. The bubble is expanding. Oh, there it goes, yeah. The whole eastern United States. Okay, that's 3x speed. That's actually incredibly fast. This is something else to witness. This is on par. This is on 1 second per second. And it's literally just 1 second per second. That's frightening how fast the shockwave is traveling up. The entire region around the Gulf, the entire southeastern or southern United States is underwater now. And now we have, I mean, what is this debris? Oh yeah, I haven't even got the 3D view yet. Look at that. Look at the three-dimensional view of the ejecta. All the crust, Earth's crust, that would have ejected into space. on this scale right here, it's so it seems like it's moving so slowly. And then once we get really close, you're going to see just how fast it is. And just how devastating a little 6-mile wide crater can be on a 10,000-mile wide Earth planet named Earth. So we'll speed it up to get a little closer, but we're gonna watch the effects, and we'll do like 3x or 2x. Maybe some nice even numbers so I can quickly get back to where we're trying to go. Okay, cosmically, it's like you can barely, if I take the trail off, you wouldn't even be able to see it from this scale. The game didn't make a point to enlarge objects for the sake of, visualizing it, because it is a visual medium here. This is so incredible. Yeah, maybe that's a good angle to have right there. Alright, we are approaching it in real time now. It's not exactly where I wanted it to hit, but it's pretty darn close. So we're going to see just how devastating this was. Just imagine. Imagine looking up and seeing this thing coming. Being on the north and the Americas. Oh, we just lost it. We lost our POV because we lost the asteroid. Alright, we're gonna zoom in here. You can just see how devastating it is instantly. Within seconds, the shock wave has already traveled hundreds of miles. Alright, let's zoom out here. There we go. The effects of the impact on planets, they for some reason keep propagating even when you mess with the time, so I'm trying my best to give us a good view here. Alright. Trying to give us a good three-dimensional view of just how high these fragments, these what are called ejecta fragments, are being launched into the air. Look at these. And I imagine this is similar to what it would be like if, God forbid, an asteroid ever hit Earth again and we're not able to deflect it. Just look how high this is going. It's going hundreds, if not thousands of miles in the air, beyond the air, out of the atmosphere. And the site it's propagating. It's already swallowed up all of Central America. You can see. And the wave has already covered Mexico, Texas, Louisiana, Florida. And it's Louisiana's flooded. Central America has been wiped out. I'm assuming that's, yeah, the atmospheric shock wave right there. And the water's coming right kind of in front of it. Obviously this isn't super, exact and realistic, but it's pretty darn realistic. Alright, I just want to, try to get three-dimensional views of how high these fragments are shooting in the air. Because you gotta remember, a huge part of the devastation is the fragments that rain back down on Earth. I don't game, so I'm definitely never gamed with the PC, so I'm still trying to figure out how to manipulate the keyboard and the mouse controls at the same time. Alright, so again, this is in real time. The devastation is... So the flood has now wiped out the entire southeastern United States. It's working its way up into Mexico, which I understand a lot of central Mexico is actually pretty high elevation, so right here, the Rockies and that are going to take a while to actually be flooded out. Let's look at Earth, and I don't know what's going on here now, but let's open the properties of Earth and check out the heat map, see what's going on with that. Composition. Let's check out the layers. Oh, we see Earth is already heating up. The minimum temperature is rapidly increasing. The maximum temperature is decreasing from, I think, about 1300 degrees at the impact site. Overview. The average temperature is 12.9. That's going to be increasing. The impact site is obviously we see the gas pressure expanding. Look at that. I'm not sure what that is. If that's fragments coming back down or what. What's going on with that? Oh, there we go. I'm finally learning how to use this. Alright. And look at these. These are... Well, Earth's radius is about... Its diameter is about, 8,000? So Earth's diameter is about 8,000 miles, so its radius, half of it, is 4,000 miles there. And so that's about 2,000 miles. I would say it's a quarter of the diameter right there. The ejecta launched into the atmosphere beyond, well beyond the atmosphere, I guess, in reality. So let's check out the rest. Just think about that. That's so incredibly high into the air. That's so powerful. There's chunks hundreds of feet across, I'm sure. I'm using freedom units, by the way. I guess I'll stick with miles and feet. And being ejected, you have stadiums are now, 4,000. They're doubling their distance. And it looks like the simulation's simulating the fragments falling back down onto the impact site and around it. I set this up so the impact happened bright and early in the morning. So, oh, what did I just do here? I don't know what that does. C. I just hit the letter C. I don't know what kind of shortcut that was, but it threw us right into the fray, didn't it? Yeah, look at that. You can see everything. Oh, that's awesome. You can see the whole planet now. Okay, let me zoom out. How do I zoom out of this? There we go. Okay. Now I'm zooming out to the whole planet. On these maps here, we can see. What is that one cold spot? What is that random cold spot? Oh, there we go. That's kind of cool. The 2D profile composition. Oh, I didn't realize I could do all that. That's pretty neat. See if the elevation got changed. Is it? Alright, so it's wiped out. I haven't even been paying attention to what's actually going on. So is that Alaska? I didn't randomly get out. Move over to the Pacific, did I? Yeah, there's Newfoundland, Eastern Canada there. Wow. Yeah, let's just look at the map. Okay. The entire North American continent is underwater right now. So it doesn't look like the elevation changed. So I'm assuming, that doesn't mean that. I'm assuming that means that, the land beyond, whatever, like 100-mile radius of the impact isn't actually affected. It's just the atmosphere and the water washing over everything is what's causing the ocean to increase. That is incredible. And again, remember, one thing that this isn't showing is look how much it's. I know Newfoundland sits pretty high up too. Look at the water just still coming up. All this is going to be burnt. There's going to be a massive wall of hot ionized gas, essentially, almost plasma, I guess, that is concentrically propagating out like the world's, the largest ever nuclear explosion. And it's just devastating. Burns, increases the temperature, 13.7. It burns the entire planet. And within hours. So it's, alright, we're doing 25x now. So, now we can see the Earth rotating in real time. Or not, we can see, look at that, we can see the fragments landing, the ejecta fragments landing on the other side of the Earth. In China, Australia, Indonesia. That is nuts. Imagine that. Imagine being in Australia or, somewhere else, and it's just the middle of the night and you just see, you don't have any sense of an impact. You have no tsunami. Maybe the atmosphere is lighting up with auroras or something, but you have no other warning sign, and you just started getting, the sky just starts lighting up with football field size chunks raining down. Let's fast forward to see if anything else happens. Oh man, the surface temperature. Oh no. Okay. I just want to see the impact site. Let's see. Okay, now look at that. We're already hitting Africa. It's getting swallowed up now. Oh, the entirety of North and South America is just gone. Bye-bye. That is incredible to think about that. Let's 10x that. Okay, let's have that. Just 5x it. So if we watch our map up here, that one little asteroid did all that and paved the way and killed out such a huge chunk. Let's lock onto Earth here. A huge chunk of what do we call it? The biosphere. Surface lock, there we go. Alright. I wonder how long it would take if we jumped it up to, days per second, I guess. Water is still eating away at the planet. I just wonder how long it would take for the continents north, for the Americas to come back. You see the climate shifting, it's 14, basically 2 weeks per second now. 2 weeks per second. Okay, let's just go crazy. How many years does it take? Look at that. We have years where it's just the green. It's just died out. Oh, it became a snowball. What happened there? Okay, I guess maybe that's just because we don't have a sun. That's funny. Okay, fair enough. Maybe we should add one. Let's add. I think I already have. There we go. Scuti is the largest known star. And we are going to put it. We're going to put it 120 AU. That's the edge. It's the boundary where our solar wind stops. It's the boundary of our solar systems. Basically our solar bubble, so to speak. Let's put it there and see what happens to Earth. Days per second. Let's go back down to minutes per second. Alright. towards this massive star. Now, that sun right there, this new sun, UI Scuti. Oh, okay, it just jumped us right there, didn't it? It's only 9 times the mass of the sun. It's only 9 times, but its radius is 8 times the, if we can do that in souls, it's 8 times the distance, 720 million miles wide. That's baffling. That boggles the mind. 700 million miles across. And that's 2.4, 2 million. Yeah. 2 million times wider than the sun. 2 million times wider than the sun. I have a weird tick where I have to type the word sometimes. I'm compelled. Alright, sun diameter versus. So the sun is I'm confused. That would mean UI Scuti is like 1 billion miles across. Or more. So the sun is 860,000 miles. That's, over 750,000 miles across in diameter. I'm not the first one to look this up, obviously. The UI Scuti has a diameter of 2.38 billion kilometers. I don't mind it not being in freedom units because it's such a large number now. But that would be roughly 4 billion miles across. 1,700 times the size of the sun. What? 1,700 times the size of the sun. I guess my math was way off, I thought. Yeah. It was e to the 6. Oh, I let the simulation run over here. Oh no, it's not. Okay, cool. We should see its temperature start to increase now. But yeah, anyways, I guess the point of all that was, let's get off surface lock here. To just try to put into perspective how massive this object is, UI Scuti. It's 120 times in this simulation further than the sun. So from this perspective, we would be inside UI Scuti right now if it were where the sun is, if it were the same distance, if its center point, I guess, it would be, was at the same distance as from Earth as the sun's center. And, but instead, it's 120 times further from Earth than the sun is. And it still looks, I don't know what, like 10 times larger. Which makes sense. That's about, multiply those, that's about 1,700 times. It's on the let's see if we surface lock this. Although we miss out on that beautiful UI Scuti glow. But we can see there. Let's just increase it. Let's go crazy. A little strobe effect here. Okay. There we go. And now we see how rapidly, so at I gotta change that. Target seems to be auto. There we go. I wish the units would. Oh, there we go. Okay, thank you. I literally was just asking for the same, the exact feature that was available. That was nice. Thanks, Universe Sandbox developers. Okay, so we're at like 20x speed or something like that. 560. No, we're at like 500x speed. 5 minutes, 8 minutes per second. 60 seconds times 8. 480. Yeah, something like that. And we can see the Earth it's still warming up. But I love the geologic timescales on this too. How accurate it is, because it would have to be, we have an accurate distance, we have accurate times, accurate energies, accurate distance and size, accurate energies, accurate, lots of accuracies, I guess is the point I'm getting at. But we also have accurate geologic time here. It shows how long it would actually take for atmospheric changes to happen if you were to replace our sun and put it, or replace our solar system with one UI Scuti was at the center of. Yeah, that's actually, that just reminded me to check out the Goldilocks zone of UI Scuti. Let's give it a shot. So let's go. Zoom way, 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 way out. And there we are. View. I forget how you do that. Habitable zone, maybe. I think that's how you do it. Oh, look at that. That is so incredible. That gives you an idea of the habitable zone. So Earth is going to get burnt. Inevitably. It is well within the danger zone. See right there, that's an example of just how much larger they exaggerate the size of Earth from larger distances, so that you're able to, still make it out. You're not just flying blind, but in reality, Earth would still be, even this far away, would be a pinpoint. You wouldn't be able to see it. But, there's Earth. Let's see how it's doing. Oh, it's starting to heat up. But to give you guys a perspective, again, it's all about relativity. Otherwise, this just, it's meaningless. If we add a sun, you can see it's habitable zone too. So, in just like a solar system. Okay, I just added a solar system on accident. That's funny. Alright, but yeah, okay, that's a great, it's still a good demonstration here. Let's highlight the sun. Okay. Look at the sun's habitable zone, which, look, would Jupiter get blown up, or that's just, okay, it's just inaccurate, all its moons, right, down there. That's awesome. Are those really all Jupiter's moons? No way. I know it has like 60 moons, but is that 60? That's insane. That just seems like a lot. It's got its four main Galilean moons, the ones that Galileo saw 500 years ago. Io, Ganymede, Europa, and Callista. Anyways, I should have named this channel I Digress. Okay, so here's the sun. And we zoom in. Whoa, shit, I'm sorry. And we zoom in and we check out. We check out its habitable zone, which Earth and Mars. Earth is just in the habitable zone. Venus looks like it's just out of it. And Mercury is well out of it. And Mars is actually looks like it's perfectly in it. I'm going to go down here and add a grid again to help us get perspective here. So AU is the distance, 90 million miles about, between the Earth and the Sun. And on distances on the level of the solar system, smaller than interstellar and intergalactic distances, AU is one of the biggest, one of the primary units you count in. So if the distance from the Sun to the Earth is 1 AU, and then Mars is about 2 AU, Sun to Jupiter is about 7 or 8 AU, I think, something like that. So when you zoom out, there we have Mercury, Venus, Earth, Mars. If you keep going, we have Jupiter and Saturn, about 7 to 10 AU. If we keep going out, if it lets us. Then we have Uranus and Neptune at roughly 20 to 30 AU. And there's Pluto and Neptune right there, so that's Pluto marks the beginning of the Kuiper Belt. The edge of the solar system is about, has many edges, but the end of the solar bubble, essentially the boundary at which the interstellar forces start to overcome the solar winds that stabilize the interior environment of our solar system, and at about 3 times the distance of the Sun to Neptune and Pluto. They're about the same distance from the Sun. And so that's 3 times 30 AU, about 90 to 120. 3 to last episode about the birth of the solar system with explaining can fit, won't even begin to break the minimal boundary for the habitable zone of UY Scuti. So that's incredible. And we can see, zooming out, you can hardly even make out as we zoom out and start seeing the red and green habitable zones. You can hardly make out our entire solar system. And looks like 668 AU is roughly probably between 5 and 900 AU here. 800 AU is what's habitable. It's where we would have to put Earth to not fry around UY Scuti. Okay, so we return to the solar system now, the regular. No UY Scuti involved. I wanted to mess around with some more impacts. Because it's fun to blow stuff up. I think it's really fun to imagine what it would be like to see an asteroid fall from the sky. Alright. Well, that's in orbit now. Okay. That's in orbit. We don't want that. Now, let's launch one right here. 3 kilometers per second. Let's see. I think the average Earth is going 30 kilometers per second. Asteroids, the most common type of impactors, slam into the Earth at an average velocity of 18 kilometers per second. Short period comet impacts with the Earth are less common but have higher impact velocities. 30 kilometers per second. Look at this. There's a lunar impact. Long period comets are up in the 50 to 70 kilometer per second range that would devastate Earth, even at like a few hundred feet across. So obviously it's a high priority for us to figure out exactly how to get to asteroids, spot them before getting to them. Asteroids and comets in particular, but I guess asteroids are much more in our blind spots than comets are, because maybe because they off-gas more, so they're more visible. this one's pulling a sneak attack. It's gonna hit Earth at night. How? I don't know how large these guys are. Oh, that one's already about to hit. How large is this guy? 103 kilometers. What? Its mass is kilograms. 103 kilometers. This is just a rock particle. Are we not calling this an asteroid? Why not? Okay, so Earth is about to get destroyed. By this quote-unquote rock particle, which is going to be nuts. Look at this thing. In real time, it's about to destroy Earth. Imagine looking up and seeing this thing just go into the shadows like that. Oh my god. Imagine being, oh, look at that. 100 miles from it and just seeing it disappear. Get closer and closer until it looks like it's obvious. It's gonna hit Earth. And then it just disappears over the horizon. Alright, let's see what the other one's doing. Has it hit yet? Nope, it is not. This one's way behind. Alright, let's see what this one does. Whew, I already cleared out the atmosphere. 15 minutes per second. And the impact site is just witnessing dawn. It's a new day over there. Where's the other one? So it hit what? Where did it hit? Just the middle of the Pacific, I guess. Did the other one already hit? I'm confused where the other one hit. Alright, let's restart. I'm gonna send a massive we're gonna go 5 miles across. Let's go ahead and zoom right into Earth. Alright. Alright, random asteroid, you are up. Let's impact in the middle of the ocean. We're gonna make it, let's see, it was 6 miles across. Let's make it 100 miles across. Or 50. Let's not go too crazy. They don't have miles, okay. it's at half speed right now. This sucker is headed for the middle of the Atlantic. Let's go to 1 second, real time. And just again, that's terrifying. There's no angle of incidence, so it's a direct, maybe a 90-degree angle, oblique. What's the word? Orthogonal. It's slightly off, maybe 15 degrees off. Let's see. Alright, so here we go. Here's the impact in real time. 20,000 miles per hour in real time. Ooh, and there it goes. Gouging out the Earth. This is a 116-kilometer wide asteroid impacting the Earth in the middle of the Atlantic in real time. And its shockwave is already 500 miles easily in diameter. Okay, let's see how it impacts. How quick, just like, you know, from out here, it doesn't look that quick. Definitely from out here. But when you zoom in and realize how large of an area that really is. How devastating that would be. Alright, so I just want to see how it's going to affect Europe and Africa here. Alright, so we're going to do exit. And then you see, just in real time again. This isn't like, you know, TV or, you know, any really good quality, I guess, for 2024, but the graphics still get the point across, I think. Okay. You just see this massive, so I guess that's the rebound right there. It's going to displace just hundreds of thousands of thousands of square miles, or at least hundreds of square miles, I guess, displacement. It's forming a crater ring. And obviously the shock wave is just devastating everything. The entire western, northern hemisphere right now. Alright, so if we speed it up, we can see all the ejected fragments now raining back down on Earth. There's one destroying the Africa, West Africa. There's a couple raining down right there. That looks like it's aimed right for New Zealand. And if we speed this up, we can see just what that, no, it doesn't look like it's expanding. I was gonna say what that shockwave's doing, but look at it glow. Just the black body radiation of it. It's just glowing as it goes into night. Oh, that's incredible. Alright, let's go to the surface log. Oh, I can just do it from up there. Alright, cool. Okay, well it's not propagating like I expected it to, so we're gonna have to reset this and do something bigger. I want to see true destruction and watch how the planet interacts. Alright, so I abandoned all attempts to try to impact the Earth with small objects. But then I thought, alright, why don't I explore not just increasing the size, but increasing the velocity? So we increased it for the Chicxulub. Is it Chicxulub? I feel like that's the wrong pronunciation, but Chicxulub crater, we increased it to 6 miles wide. Increased the speed from like 2 to 20 kilometers per second. But now I forgot that you can play around with light speed in this game. So that's what I want to do. I want to take an idea that I got from Gray Still Plays. He's a really funny YouTuber who messes around occasionally on Universe Sandbox. And let's decrease the time, make a tiny object, but mess around with the overall energy, the kinetic energy it delivers upon impact by increasing its speed. So we're at 2 minutes per second here. I can launch this. Slow it down. Increase that simulation speed. There we go, that's better. Let's decrease it a little more. I want to see what would it be like at ground zero, getting hit by a 50-kilometer wide asteroid traveling at 90% the speed of light. Let's find out, guys. Here we go. Into the atmosphere. We have entered the atmosphere and the planet. There we go. Oh, it has ripped. Alright, let's zoom out a little bit, get some perspective. And remember, this is 0.05 milliseconds per second. This is on this order of nanoseconds. It's like 50 nanoseconds per second. It's happening pretty fast. It's happening pretty fast. Alright, 0.1 milliseconds. 1/10,000th of a second. That has happened. On the order of 1,000th of a second per second. Let's see what happened on the backside. Oh, it's just the whole Earth. Okay. I think we opened up a hole in the Earth there. And the Earth looks pretty devastated. Oh, look at that. That's awesome. That's pretty cool. Oh, nice. You can make that bigger. That's awesome. I didn't know you could do that. Yeah. Okay. Well. Alright. That's about that. We have a 50,000 degree Earth. Finally got some results. Man, that was a little disappointing. Having to ramp up the parameters that much. Okay. Last thing I want to do, well, second to last thing, is yeah, there we go. Look at that. Solar system is something along the lines of this. I want to play around with objects in disrupting the solar system. Look at that Jupiter. Betelgeuse is so big that it would essentially expand. Its surface would be all the way out to Jupiter. Oh, so they just open the simulator. Well, I guess that's all you can do. The red supergiant Betelgeuse. Let's see what Uranus. Like Taco Tuesday. Like the night after Taco Tuesday. Uranus is heating up, guys. Alright, so Betelgeuse is a red supergiant. Mercury, Venus, Earth, and Mars all have orbits smaller than Betelgeuse's radius, so they would have already immediately been inside. And is it? 11 times the sun's mass. But even Betelgeuse isn't as large as our UY Scuti. Look at that. I really like the idea of replicating like what it would be like to live on a planet with two suns, especially dim suns, because something like about dim suns just seems really, appealing in a fascinating sci-fi kind of way. So if we're gonna put Earth out here, way out here, that's 70 AU. Well, let's check out the habitable zone. We could at least attempt to have a habitable Earth. So habitable zone, okay. The Betelgeuse is 120 AU. Again, 100, that's about the extent of the actual solar systems, proper, I guess, before it starts to get swamped by the interstellar winds. So we got Earth way out here. Maybe in orbit. It appears to be in orbit. Let's see. Well, let's slow it down. Let's slow things down a little bit. Alright, so the red supergiant, there's something, just so calm and fascinating and comforting at the same time. This weird mix of, I guess, what I'm trying to do with my channel. About, orbiting really far. It's like you zoom in. And you look and you pan across. Let me get rid of the habitability. The habitable gas over here. And to look at Betelgeuse. That's so incredible. So if we were to put the sun where Betelgeuse is, it would look like a star. It would be so far away. It would be 4 times further from Earth than the sun is from Pluto, actually. So let's do it. Let's see what it would look like. So we got the sun right there. So 10 AU, 120 AU. And let's see the luminosity that the sun would give Earth. Let's fly into it. Wow, almost nothing. That's really interesting. Let me make sure the view is right, so it's realistic lighting. Yeah, realistic. That's really interesting. So let's find out how dim the sun actually looks. Yeah, look at that. It basically looks like a really bright star. Alright. So I want to 1,400 light years from Earth. Wow. That's awesome. That's an actual picture of Canis Majoris right there. Canis Majoris. That's on the star's been known since for over 3,000 years. I love that. I love that we used to, humans have evolved staring at the stars, not only using them objectively as guides in the night, but as projections of our stories onto the sky. One of the few things that it's over the span of even hundreds of generations of humans is fixed in nature. RVY, okay, that was not, I guess the constellation's been known for 3,000 years. VY, Canis Majoris, the star's an extreme oxygen-rich red hypergiant. It's one of the most luminous and massive red supergiants. It's one of the most luminous stars in the about 17 times the mass of the sun. Surrounded by a circumstellar envelope. It's part of a star that has a roughly spherical shape and is not gravitationally bound to the star core. Usually circumstellar envelopes are formed from the dense stellar wind, and they are present before the formation of the star, caused by its mass loss. It was one of the first radio masers ever discovered. It's embedded in a large molecular cloud. So it seems like it's way too chaotic to have any planets with any possibility of life around that star in that cloud. The radius is roughly 1,400 times that of the sun, which is close to the modeled maximum, the Hayashi limit, a volume nearly 3 billion times that of the sun. A volume of 3 billion times the sun. Wow. The speed of light would take 6 hours to Earth's just gonna get sucked right into it. Oh, whoa. What an interesting orbit. Wow. Okay, let's slow down here before anything crazy happens. Because this is exactly what I wanted. I didn't plan this. I'm not that sophisticated. Oh, yeah, of course, the Earth is a ball of 300-degree gas, but whatever. I wanted to look at its sky. Just imagine being in a system like that and looking up at the sky and seeing two red hypergiants. It's not exactly Tatooine, but I think it's still very cool. The magnitude of things out in the universe always stuns me. What I wanted to finish up with, there's a lot of cool little, simulations, pre-made simulations, and a couple tutorials that we could do, but I did want to now let's check out the Constellation tutorial. I did want to do that one. Okay, here we go. Alright, check it out. So, the stars and constellations may look like they are situated, nested with, in proximity to each other. But, this one here, in which Betelgeuse is actually a part of, is a simulation, but it's an accurate depiction of three-dimensional, grid system, showing you the spatial separation between the stars in a very popular constellation, and it's going to show us how it evolves. So there's Betelgeuse. Right there. Here's a hint. This constellation's visible in both the northern and the southern hemispheres. And here it is. So Rigel is a pretty big star, and Betelgeuse is the top left corner. The top left shoulder, I guess. For you guys, it would be this one, right? Of the Orion Nebula. Select, expand. Oh, it's telling us to turn on the constellation labels now. It says Orion. Constellations are only symbols, images created from stars from the perspective of the Earth or the Sun, if you're, averaging distances there in the cosmos. So if we lived in a different part of the galaxy, the tutorial's saying, the constellations would be viewed, these stars, and they're not star groups, they're just groups. Us projecting 3 dimensions onto projecting a 2D surface on which, from our perspective, all stars appear to lie on. But in reality, they're really way further apart than I, used to guess. And now it's going to fast forward and watch how these stars, given their current known velocities, which is a fascinating feat of human, intellect, how they discovered velocities of stars, given that over any short span of just even years, the stars' positions do not perceptibly change. So how the hell do we know what the velocities are? And I think it has something to do with Doppler shifts. It has something to do with statistics, but I don't know much more than that off the cuff. It's fascinating, though, how they're able to predict, at least, what these stellar velocities are. So, and they project them, extrapolate them into the future, and we get this. Let's press play. And we see, from our perspective, this is how the stars are going to evolve. It'll take about 350,000 years for Orion to become unrecognizable. But even then, the four main stars, really, it still has roughly the same shape. And I know the sword down here is a star-forming region, so maybe some of that gas will have dispersed and cleared out, and it'll seem like it's brighter, maybe, or maybe dimmer. I don't know. If the gas is no longer reflecting any of the light. But the stars aren't physically related to each other. Just like one of you corrected me on the birth of the solar system video, I know we formed within a constellation of stars, or, a group of stars. The sun did, and the sun in us ultimately formed, 5 to 10, 5 to 7 billion years ago, I guess. But the orbits around the galaxy, we've made about 20 orbits around the Milky Way core since then. So all the stars since then have, as they go, they've drifted away, dispersed. So it's interesting how stars do, especially the dynamics, the galactic dynamics, how it affects stars, how arms can form, and you have star-forming regions within galaxies. You have bright bands, you have denser cores, denser regions of arms, looser, you have more eccentric orbits, more inclined orbits that vary off the plane, but still most of them are within the orbital galactic plane. Even though constellations aren't physically significant, they're still helpful for finding your way around the sky. Try loading the complete set of Western constellations. And watch how their positions change over thousands of years. Can we reverse that? Alright, we can. Cool. Alright, let's reverse it. Alright, get back into your normal shape there. There we go, something like that. Nice. Okay. Oh, there it is, alright. That is really interesting. Oh, okay. That's the sun. And we can see slowly how the positions of all the Orion stars are changing over time, over 10,000 years per second. Maybe we'll have visited some of those stars before they even reach their positions right now. That's cool. And the three-dimensional view looks like this. This one's far away. So what are we in light years? That's 100 light years. No, that's 1,000. Possibility of interstellar travel is so, it's really fascinating. It's also something interesting to think about. Just what kind of new technologies, if we don't wipe ourselves out with AI or nuclear weapons, what we will have achieved in just the next 100 years, and then put that 2, 3, 400 years into the future. I have no doubt in my mind that we'll have unlocked fundamental patterns and relations between matter and energy in the universe to be able to manipulate the space around us to put humans in another star system, on another star system's planet, a habitable one, hopefully. Okay, well, this has been fun. I hope you guys enjoyed this really off-script adventure aesthetics and styles, and like I said before, their shirts are seriously comfortable. So give them some love, and thanks again, Into the AM. Thanks for watching, guys. Thanks as always for joining. Thanks for the love. Thanks for all the comments. Thanks for the support. You guys are always super, super positive and encouraging, and I hope you guys enjoyed this one. Let me know what you did or didn't like. Let me know if you want another Universe Sandbox video, because I can make it happen. There's still lots left to explore. I had fun. Hope you did too. Take care.